Hello everyone. Thank you for coming, and sorry for the all the mess. Today we have Minji again presenting. Everyone knows him again, but I'll just introduce a couple of lines. He's a research associate at Oregon State University, and he'll be talking about how to implement parallel computing in OpenSees. Python version, Tickle version is well established, but we don't have any idea. It's very upcoming in Python version, so he decided to talk about it. So it's gonna be very interesting. Thank you, Minji, for presenting, and it's all yours now.
Okay. Yeah. Thanks, baby. Thank you all to have me here. It's my pleasure to present again here to everybody. So today I'm talking about the parallel computing in OpenSeesPy. This is not new because it's actually on top of the OpenSees parallel functions. If you have used OpenSees SP or OpenSees MP, this will be very similar to that, but a little bit different. So I will go with 3 sections. Yeah, by the way, this is Jupyter Notebook. I guess most of you know it. So 3 sections. So first I will introduce how do you generally run OpenSeesPy in parallel, and how do you run independent analysis like parametric study. So these analyses are independent to each other, but run at the same time. And lastly, if we have enough time, I will talk about a single analysis, maybe with a large model, how to decompose the model in parallel. So first, about how to run OpenSeesPy in parallel. So when we talking about parallel computing here, we mean multiprocessor parallel computing. That means you have multiple processors available. So this model is different to those called multi-thread model. So for a multi-thread model, you have one node or one computer and with multiple threads. And those threads share memory. But for a multi-processor, each processor has their own memory space. They pass messages with each other. So the advantage is you can come across different multiple nodes or computers or even over the network. So OpenSees is built on the multi-processor model. So in order to run OpenSeesPy in parallel, currently you have to use Linux, maybe Mac in the future, but Windows, I haven't figured out how to do it in Windows. But yeah, you have to use Linux. Any Linux distributions should be okay, like Ubuntu, CentOS, etc. And also you need MPI installed for your Linux system. You can just go to MPI-CH. They have the instructions for different Linux platforms. You can just install for your own Linux. So MPI is a program to launch multiple process for one program. If you have MPI installed, you can always check its information. So this is my MPI installation. If I just run it, it print out some information. So my version is 3.3.2. This might not be the latest version, but it's enough for run OpenSeesPy. Yeah, you can just check your system to see what version you have and what's the installation location. Yeah, so then the first example I want to talk about is a hello world, right? That's always the first one to do for any problems. So first is a simplest example here. So this is notebook. However, you cannot run MPI or the parallel computing directly from the notebook with the script. So that's the script in the hello world.py. So it simply load the model node package, get the PID. So PID is the process ID, since we have multiple processes, and each one has an ID. It starts from 0. And NP is the number of processes. And each process will print just a string to the screen. It says hello world from process PID. And the process 0 will print the total number of process. So this script is very simple, but if you just run it here, you always have one process because the notebook always launch one process. I know the notebook has a parallel version, but I never used it. So the way I call this parallel computing is I use another cell to do an external program call. So I locate the MPI exec. So this is the launcher. And give it argument is number of process you want to launch. And the rest is the program and arguments for Python. So basically I run Python with the hello world script. So if I run it here, you can see it prints out the hello world messages. You can find that the first one is not the 0 because each process is independent, totally independent to each other. So the launching order is undecided, and it's actually random every time you run it. See, every time the order of process launching is different, so your code should not depend on the order of the processor launching. In this case, the processor 1 is launched first, so it prints out the total number of process NP even before other process print their messages. And you will also see the terminating message. That is when each process, each OpenSeesPy process ends, you print out the terminating messages. So this is the simplest one I can have. So if you can run it like this, you already have the parallel function in your computer. Usually nowadays the laptops comes with like 4 or 8 threads or processors. You can use all of them or part of them. You can even use more processors than you have. Like I only have 8, but I can launch 20. So if you launch more processes, it means it it may launch one after the other multiple times. Okay, so this is a simple example. Let's see a little bit more complicated example. Yeah, the outputs are different each time. A little bit more complicated. As we said before, the multiprocessing model, they need passing messages between processes. So OpenSeesPy has 4 basic commands for message passing. So it's called send, receive, barrier, and broadcast. So the send is just for one process. to send information to another processor. And the other processor need called receive explicitly to receive the data from the other one, from the same. So it's very, very important that you need to match the send and receive. If you don't receive it, or if you didn't send, for say processor 1 is sending, should send to processor 2, and processor 2 is just waiting for the message from processor 1, but processor 1 never sent it, your program just stops there forever. And barrier is a synchronization method to wait for all processors to reach to that point. And broadcasting is a convenient way for one processor to send information or broadcast information to all other processes. Here I have another script, hello2.py, a little bit longer. So this script has 3 parts. So that this is the one part. For the send and receive functions, they can send 3 types of data: string, integer, and floating number. So now I'm just showing the string sending. So in the first part, I call it random sending message because so the order of calling from different processors are random because you cannot assume which one is called first. So now we have a if-else statement. So if this is the processor 0, so usually we use 0 as the main processor. If I am 0, I'm receiving data from all other processors, from 1 all the way to NP minus 1. But here I don't say which one. I don't need to know which one I'm receiving. So I put any parameters. I can put other values, say dash PID 0 or 1. That means I'm receiving from processor 1. But here I'm receiving from any processors. So for the main processor, once I receive one data, I just print it. If I am not the main processor and other processors, I'm sending data to processor 1, and the data I'm sending is just hello from this my PID. Let's run this first. Oh, I should not. Yeah, so let's run this first. I cannot run here, run from here. So from random, so the processor 0, main processor, print whatever he received from other. So it's from 1, 2, and 3, because I have 4 processors. If I run it again, same order, another one, yeah. So in different times I run it, so this message are different. So this is the first part. And the second part of the script is I want to receive an ordered message. So the only thing I changed here is from any to I. Although I cannot decide the order of sending commands are called, but I can say I just want receive from processor 1, because this is a loop. So I'm just waiting for processor 1 to send me data. Even the processor 2's data arrives first, I still wait for the processor 1's data. So this will give me an ordered messages from from the data I'm receiving. So let's run it here. So you can see the random data are just changing, but ordered data are not changing. So it's always 1, 2, and 3. The last part is about the broadcasting. So the broadcasting is for one processor broadcast to all others. So my main processor 0 will broadcast one message to all other processors, and all other processors call the same function to receive the data from the one that is broadcasting. So, and this shows the results. So all other processors receive data all from the processor 1, because processor 1 is broadcasting. Yeah, I can run multiple times. So it's just the random part is changing, but the other two are not changing. Okay, so this is very simple introduction to the parallel functions. Although these functions are fairly easy to understand, to use, you actually can use these simple functions to write, I think, fairly complicated applications. Okay, yeah, let me go to next section, how to run independent analysis in parallel. So far we know about the message passing, how to launch in parallel. And next, we need to do analysis in OpenSees. For that to happen, so first, let's talk about the parametric study or parametric analysis. So for parametric analysis, or sometimes called embarrassingly because there's basically no message passing between processors. The purpose is I have a list of parameters. The parameters could be like elastic modulus or some geometric parameters, or for your materials or anything. I want to study how this parameter is changed and my results are changed. So in order to do that, usually you just run the same analysis multiple times if you have only one processor, but we can accelerate it with multiple processors. And each processors run a single and independent analysis. And each analysis has a different parameter. Say we have a different E for each processors. And at the end, so in the between, that's same for all processors. But at the end, all processors gathers their data back to processor 0 or to the main processor, and the main processor can print the data for different parameters. So you can see the only message passing is at the end here, to gather or reducing the results to the main processor. Let me run it. So independent analysis. Okay. So now I also launch 4 processors, and each processor takes one elastic modulus value, a different value, then put this value into the uniaxial material. So so now I have 4 models, and each model has a different E. The result shows the processor 1 has this E, and this is displacement I got. Although this the order is not that important. The important part is I get the different results from different E's. And then my processor 0 gathers all results I receive from each processor. And at the end, I plot number of processors, the processor ID with the displacements. So all the results should be here. So here's the results. This is PID, this should be integer. So this is processor 0, processor 1, 2. You can see the, so then I have decreasing nodal displacements with higher elastic modulus. So if you have a lot parameters, like when you do the fragility curves, so this will greatly accelerate your analysis if you have a large number of processors. Or even you just have 4 or 8, it should accelerate. Not as fast as 4 times, but it will be close, like 3.9, 3.8 times faster if you have 4 processors. Okay, so this is the independent analysis. And the last part will be the single analysis with large models in parallel. So this kind of analysis is different to the previous one because now I just have one single analysis. And maybe this analysis has a very large model. My one processor solves the equation very slow. So what I want to do is I want to decompose or split the large model to smaller models. However, those models are not independent to each other. They are still connected to each other. So as you can imagine, that will be a lot message passing between these models, especially in the solving stage. So in the solving stage, imagine you have a large stiffness matrix, and part of this matrix are in this processor and another part of the matrix in another processor. And when you're solving this big matrix, you need to pass back and forth a lot of data. But fortunately, most of this message passing has been written for us. For Linux, we have a solver called MUMPS. You might have heard it. So MUMPS is a parallel solver, very fast. So it's a direct solver, but it's very fast when you use multiple processors. You need just give it your big matrix and the partition of the matrix, and this solver will just do the rest work for us. So this part has been taken care. And other parts, including numbering our equations, because our model in different processors, and if we want to number those equations, some of the nodes are shared by 2 processors, so their numbering should be same. So this is also another very difficult job, but that's also written or built in OpenSees. Now I'm using another number called parallel RCM. It's a parallel version of the RCM number. So number system. Okay. So the only part we need the users to participate in is the partition part. So how do you want partition your model? Because generally we don't know much about individual or your model. So you pretty much have better idea how to partition your model, because if your model is naturally divided, has only few points connect, like you have a model has two major parts, and they only connect in few points, then you know that's the perfect place to divide the model. So in OpenSeesPy, we provide two approaches. One is automatic partition of the model. The other is manual partition of your model. So if you're very confident, know your model, you can always use the manual. And if you're not sure, and you just want to let the program do it, you can call it automatic partition. So the automatic partition is very similar to OpenSeesSpy, and manual partition is similar to OpenSeesMP. So that's the analogy between the Python version and the Tcl version. Okay, so in this example, what we have is the model is large, but I just want to use it for demonstration. So this is a trust model. We have 8 nodes and 13 elements. So this is the 8 nodes. We have 1 through 5 at bottom, 6, 8, 6, 7, 8 at the top, and have horizontal load. At the beginning, we say it's auto partition or manual partition, and we get your PID and MP. So this is the same to define the model, define the material. This is the same for both partitions. Then for automatic partition, so for automatic partition, like I said, it's similar to OpenSeesSpy. You just define your model as if it's a single processor analysis. You define your nodes, your elements, nodes, elements. You define your time history, time series, load pattern, the load. And just at the end, you call this OPS partition. So this function will just partition or split your model to a number of processors you have or you assign here. So this is auto partition. Or you can do a manual partition. So for manual partition, here I assume you have 2 processors, and I manually divide this model to 2 parts. So for processor 1, that's 1 part, have 6 nodes, 1, 2, 3, 6, 8. If we go back here, it's 1, 2, 3, 6, 8. So part 1 on processor 1 is the left part. And part 2, so this part 2 for processor 1 is the right part. You can see here is they share some nodes. So it's the nodes in the middle. There's 3 and 8 nodes. They are shared by the 2 subdomain or partition of the model. You have to have some shared nodes, because only through shared nodes your models are connected to each other. If you have no shared nodes, they are independent models. Okay, so then when we go here, we want to print what's the nodes in the partition 1 and what's the nodes and elements in partition 0 or partition 1. I have a barrier here because I want to wait every processor reach to this point and start print next. Otherwise, these messages are printed together. You cannot see it very clearly. Then at the end, we normally we set analysis options. So only 2 of them should be changed for parallel computing: the parallel RCM, a parallel number, and a parallel solver. I usually use MOPS. Please note that this setting only needed if you do one single analysis in parallel. If you want to do parametric study for independent analysis, these settings will be same. I think, yeah, I put parallel here, but you actually don't need parallel here. They should just the same with the regular analysis, because each one is a independent model. Only when you need partition your model and run the big model in parallel, then you need this two special setting. So there's actually 3 things to do: parallel number, parallel solver, and partition if you need automatic partitioning. I think that's fairly straightforward to follow. You don't need to change much of your model. You just only change 3 things or 2 things. Then you got a parallel computing for your model. Okay, so now let me run it here. So here I have 2 commands. So one is do the automatic partitioning. So this is automatic. This is manual partition. So manual partition are I did it. So I split to the left and right. So with my eyes, I can see that probably the best way to do it. But if you look at the automatic partition, they have a different subdomains. So the partition 0 is 1, 2, 3, 4, 6, 7, 8. They actually include everything except the node 5 for partition 1. And for the partition 2, they have 4, 5, 6, 7, 8. And this is the other partition. I don't know why they do that. Internally, we called Metis to do this partitioning. It's their decision. Like I said, if you know your model better, you should do the manual partition, because this is definitely better, because there's least connected partition if we just do the left and right. And the results are also printed here. Node 8, yeah. So they should, but whatever partitioning you use, they should print out the same results. The partitioning should not, it may change a little bit, but it should not change significantly for your results. Okay, I think I have gone through enough information, a lot of information here. I think it's time to hear some questions. Yeah, Pavan, what do you want to do?
Yeah, sorry.
Yeah. So you go to another room?
Sorry, guys. Today we have been all over the place, not very well organized. But yeah, thank you for the presentation, Minjhe. It was really helpful, and at least now people in Python version can at least attempt to do parallel computing. But you said in Linux only it's possible, right? It's not possible in Windows, right?
Not at this time. Yeah.
Okay. So yeah, I mean,
Actually, you can do it in Windows through WSL, Windows subsystem, Linux subsystem. So it's just a Linux subsystem on Windows.
Okay, so we'll just ask people to ask their questions. Thank you again for presenting it. It was really great, and hopefully it will help people who want to do parallel computing. And questions. Oh yeah, sorry, I didn't see that. What ELIF 2 in 1.2? Yeah. So
1.2.
Yeah.
0.2.
Yeah, HW. What is HW? Homework.
Hi, I was talking about the Hello World code.
Yeah.
1.2. Yeah.
Okay. So what's the question?
The cell. Can you scroll down to the cell where the code is written? Yeah, here. Here we have else if code, and in the else if code.
Here.
Yeah. Yes. What they do? Float PID, int PID. What they are doing?
Oh,
like what's their function?
Float PID. So this is just because the send and receive can send these 3 types of data. So this is change PID to a float format, to float number. Let's make sure this is an integer number. Yeah, because Python, Python, the variables is strong typed. They have type. It's not like Tcl. Tcl doesn't have different types. They all have strings, right? So this just make sure you passing the correct type. Yeah, does that make sense?
Any other questions, guys, from the audience?
I have a quick question. The bcast function, I have not seen that in the Tickle version. Is that just with OpenSeesPy?
Yeah. I add it because I find it's useful for me. So I add it.
Is that same with the partition command? Is that also unique with Python?
Yes. For Tickle, it's just OpenSeesSP and OpenSeesMP.
Okay.
Yeah.
So with OpenSeesMP, with the Tickle version, you can't partition your model?
No, you have to do it manually.
Okay, so you'd have to manually partition and then use mumps and use parallel RCM.
Yeah, but the ASP will do it for you.
Okay. Cool.
Other questions?
I have more question.
Yeah, go for it.
Thank you for the presentation. Question about chapter 2. In your example, you use only one parameter in here, Young modules. But if we want, can we set more than 2 parameters?
Yeah, you can multiple parameters. Say I equals to, I just put some random value here. And then you have to use something like I PID to get I for the current processor. But of course, you need more processors, right? So if one parameter and one parameter has 4 different values, you have 4 processors. And if I have another, that's 4 times 4. You need 16.
I see. Mm-hmm. Okay, thank you.
And we have a question on the chat. Is there a way to run analysis over multiple computers connected on a network?
I will say that's possible, but it's really up to your IT department. I think each university has their own cluster. It can run its own cluster. Yeah.
So it's possible. And
also we noticed some problems running on cluster on one of the cluster actually. We're still not sure if that's universal, but if you run cluster and you see some problems like you launched processors, and when the program ends, the processor doesn't die and stay there, please let us know. Yeah.
So in some clusters, the program just keeps running and it never terminates?
Yeah.
Okay.
We're trying to fixing that. But if you do have that problem, let us know. But we only find it in one of the cluster. There's no problem if you run on your own laptop or desktop. Only one clusters. So my guess is the clusters have a different, processor management, different to the desktops. We can fix it soon. Just a note, just a side note, if you have a problem. Yeah.
Any other questions from the audience or?
Yeah, I have a second question. Which version of OpenSees is being used here? Is it MP or SP in OpenSeesPy? Or they are used together?
Yes, kind of together. There's no MP for OpenSeesPy. Like I said, the difference is just you want to use the partition or you want to do it yourself. So it's all together. Yeah, maybe.
So during the compilation in a make file, will it be, usually there are 2 options available, 3 options, serial, second is SP, the third is MP. So what is the make def file for it?
You mean for compiling OpenSeesPy?
Yes.
You mean you compile from the source code to?
Yes.
Oh. So I think by default, if you type make Python, it will make the serial version for OpenSeesPy. And if you want to do a parallel version, you need your makefile.def to set up, all these parallel libraries, include path, this type of things, and in order to have a parallel version compiled. Yeah, it takes some work to do, but yeah, it's doable for Linux. Yeah, but if you can do it in Windows, please let me know. I'd like to learn some new stuff on Windows.
I think if it's on Windows, lot more people will be more coming forward to use it than in Linux, I feel.
Yeah, I know. But the problem is mumps, I think. I don't have a Fortran compiler on Windows to do mumps. MPICH is okay. I think the major problem is mumps. And maybe some other like scale LAPACK, this parallel libraries on Windows. Yeah, but you also can use WSL on Windows. Yeah, so it basically Linux system on Windows.
Oh. Any other question, guys? From here as well. Okay, I have one question, like which I read like on one of the groups. Like you said, like you have 8 processors, but you can give up. You give 20, right? So what will be the disadvantages if you give that way?
There's no advantages.
No disadvantages. So I read Michael Scott was like mentioning that like, oh, it will delay your process, like the speed. I just want like maybe that's a point like everyone should know because it was interesting.
Yeah, I think you should just use up to what you have. Although MPI let you choose more, I think they are just switching between these processors. Let you think you have more, but I think that will actually slow down the computing. Yeah, if you have 8, you just use 8 or less, like 6.
Okay, cool.
It's
Yeah,
like
you can't just print money, right? I mean, you gotta back it up with gold or whatever you have available, right? But Alex may know better. But go ahead, Alex.
oh, I was just gonna say it's like a professor giving his graduate student 100 papers to write. You might get it done eventually, but it's not gonna do it any faster.
Yeah.
Yeah. Actually, slower.
It'll be less focused because it's constantly switching between the two.
Yeah. I think it was an interesting question on the on the Facebook group. Like I was like, oh yeah, this is exactly what we wanted to have this section so that like people get things clarified, like these kind of things, right? So cool. And any other questions, guys, or anything else? Oh, we have.
So, Minjhe, when you right there in that cell 61, is that just your path on your local machine to MPI exec?
Right.
Yeah. So you just do like which MPI exec, and that's what you're pasting there, or what you put in that cell.
Yeah. That's my installation.
Yeah.
Yeah, but you should have your like system MPIX.
Yeah. But I mean, that's just from the which command.
Right.
In Linux, right? Yeah. Okay.
Cool. I mean, so one other question is like when you run on the clusters, like as you asked, so is it better to run like so the cluster has their own coding, right? Like you need to use their own, and you need to integrate it with the OpenSees. I know some of my friends are using Tickle version, but like if I have to, do we need to follow the same process if we are using the Python version as well?
Yeah. I would recommend Python. Right. But if you run on cluster, the problem I just mentioned, the process doesn't die. If you run with MPI execute, it never has problem. Only when you run without this, if you just run Python 3 hello.py, that might cause problems on cluster. But if you run with MPI execute, it's okay. It's guaranteed okay. Not guaranteed, but so far it's okay.
So what you showed us today will be applicable for our desktops or something, but if we are doing it on cluster, then again the process is going to be a little different to this.
I think no, it's the same. It's
okay.
The same. Yeah, on clusters you usually submit jobs, right? So when you submit jobs, you typically you give the number of processors you want, and which is the MPI execute. It depends on the cluster, but that's the typical parameter you put when you submit the job.
Okay.
So I will say that's the same thing.
Any other question, guys, from the audience? Feel free to ask. We have some more time left. If you want to make use of it. It need not be about the presentation. It can be from anything else too, because you have these people who can answer questions too.
I could just mention something more in regard to Jonathan's question. Jonathan, are you looking to run like a large model in multiple computers connected on a network, or like independent study?
Jonathan Asafa.
Yeah, Jonathan Asafa.
I am trying to run it on my own computers.
Yeah.
Connected by myself.
Is it
Actually,
a large model, or are you trying to run multiple analyses that are independent?
They are independent, actually.
Okay.
The same model with different parameters.
Okay.
Yeah, then what you can do actually is you can basically assign job numbers for each of the independent runs, and then on each computer you can run those job files in separate instances of OpenSees. That's more of a manual way to do it, but you can automate it yourself as well. But that's like basically splitting up the tasks and parallelizing the tasks. Just make sure if you do that you set up parallel folder structures so that your output files are in separate folders. So.
That's not really parallel computing though, right? I mean, that's distributed computing.
It's distributed computing, yeah.
Parallel.
But I mean,
yeah, embarrassingly parallel, right?
Huh? Yeah, it is embarrassingly parallel, but I mean,
yeah,
it still is way more efficient than in series.
Oh yeah, yeah.
Yeah, and also thank you for mentioning that the file system. Yeah, if you do parallel computing like that, you need carefully. If you save files, just make sure you don't override to each other. Yeah.
Or even worse, try to access the same file while modifying it with multiple processes.
Yeah.
You'll get race conditions.
Yeah, racing conditions. Yeah. And also, this is like. Graduate students go to everyone's computer to run analysis in everyone's computer.
Yes, exactly. Yeah, I'm an expert in parallel processing.
Yeah.
So Faisal has a point here. BO cluster can run MPI on network connected nodes. You may need to establish BO cluster first. I mean.
So that's a question for me?
Or maybe it's a suggestion for them. I don't know. There was no question mark. So.
Yeah, I think it's just a comment about I think it's Beowulf, like the old English tale, right? That we read in high school. But yeah, cluster for running MPI on the network. Yeah. Yeah, it's not a question, just a suggestion.
Yeah. Minjhe, one more thing, like, can you comment on the post-processing, like when we do use the parallel computing, like, because it looks like you're using the regular post-processing commands, right? Like matplotlib commands and stuff. So when I want, like, for example, you showed just the displacement of the top node or whatever, right? So if I want like the deformed shape of the truss, like in all the 4 cases or 16 cases, how do I do that? Like still, how do I collect the information from each model and save that?
So I mean, how do you gather all the informations?
Yes, is it the same way or like?
Yeah, you can, I think 2 ways. you can get the information through MPI. So send, receive, you send all the informations to one processor, and the one processor do the post-processing. Or you can dump all the information to the file system.
So the question is, like, for example, sometime, for example, I want to create an animation. Let's say, like, I want like all the nodes like at each time step for all that. The way you are doing now will give me the final positions or the final displacements kind of a thing, right? So if I want to track like the displacements and reactions and forces in the parallel computing, I mean, I never did this, so I was curious how to do that.
So for this parallel computing, you can imagine just different computers have their own memory and share the hard drive. So it should do as normal, but you just need to be careful. Don't overwrite your files on the file system.
Okay.
Yeah, but a comment here is, I know ParaReview has some parallel post-processing functions. Yeah, but I never tried. But yeah, it's just very information. But I think that also requires you save files in different names. So
Okay.
The ParaReview can read these files from different processor.
Okay.
Yeah.
I mean, this is something I wanted to try, but like, I'll try and see that.
Yeah, for time history analysis, so the series of data in terms of time, it's still the same. You don't parallelize the time, right? You parallelize the different parts of the model. So you need to store this time history values.
Okay.
Yeah.
Question. Okay. So does anyone else have any questions?
I have kind of a off the wall question, but Minjhe, can you scroll down a little bit for that plot?
Yeah.
This may be for the graduate students on the call. Like, so Minjhe was changing E from 3,000 to 4,000 to 5,000 to 6,000. Why is this plot not a straight line?
That's a good question.
Took me a second to think about it, but why is this plot not a straight line?
Don't ask me.
Your qualifying exam. No, not for Minjhe, but for the PhD students on the call, or graduate students.
Can you zoom up to the script for the model?
Yeah. That's the model.
It's a candidate.
So it's the old three-member truss example that has been in OpenSees since the beginning, but it's the same material for each truss element, right?
Yeah.
No, it's a little bit different, I think. No, same material, but different.
Same E for, yeah.
No.
The analysis was wrong.
No, I think it's right.
One wants to answer it.
No one wants to answer it, or
72. Load is fixed. Applied here. Back. Oh, sorry. Gravity.
What this plot is in between, like in horizontal it is PID, but what is on the vertical?
Oh, it's the deflection at
That's UX, deflection, and that's the PID.
It's not linked. That's first. Oh.
yeah. Why is it not just a straight line from PID 0 to PID 3?
Oh, I know why.
Why?
Well, just think about what happens when the stiffness goes to infinity, then your displacement's 0. So
Yeah, it's the deflection is 1 over proportional to 1 over E, right?
yeah, I don't know.
It's
I was just
inversely
thinking,
proportional, not directly proportional. Right?
yeah, it's
It's just
if you just invert that graph, then you'll get. I was thinking of force equals stiffness times x, but it's
deflection is 1 over E, proportional to 1 over E, right?
yeah. Trick question.
You're all you'll get asked this in the qualifying exam or something.
Good. Thank you.
Well, thanks for preparing me.
Sure. No, but
now we know not to put you in our committee.
It took me a minute to remember why is that not a straight line? But then it's correct. I thought it was wrong too, but then yeah.
Okay. So just be careful the pictures you present to professor.
Yeah.
I knew it was right because Minjhe did it, but I had to remember why it's right.
Okay.
Any other interesting observations from anyone else? That's really cool though. Cool. I mean, if no one has any questions, then like we will wrap it up for today. Thank you.
One more question.
Yeah, go for it.
In parallel, it was elements and nodes. What else we can make parallel? Can we put loads in parallel? Like what else can be parallelized?
So you mean how to partition the model?
Yeah. In partition, we used here in this example in partition, we made partition for nodes and elements.
Yeah.
So besides this, what other features can be included in partition?
Yeah, so mostly just nodes and elements, right? That's the parts, and the loads, boundary conditions just go with the nodes. But just one thing, say this load is not on node 7, but on node 8, and you partition it, node 8 is shared by the both parts. Just be sure the load only apply once instead of twice. Otherwise, you have a double load. Does that make sense?
Okay, thank you.
So you have duplicate nodes and elements, but not loads and constraints.
Actually, you can have duplicate nodes, but not elements.
Oh, not elements. Okay.
Right,
What
'cause
about fixities?
Fixities just go with the nodes.
Okay, so
Yeah.
only one fixity per node?
I think you can either one. So I think the program internally can decide that node is already fixed on another processor and try to match that. I'm not sure if you have different fixity for the same node on different processors. I believe there's a way to, to merge the boundary conditions. But yeah, to make sure your model is correct, just put one support or one fixity.
Okay.
Minji, to add this, like you in the above, like before, like this piece of code, you changed the E values, right? E and I, you said you can change. But can we run like for a particular model for different loads as well?
Yeah, I think.
Yeah, there you can change the loads, but not here. Okay.
Yeah.
No, here if the 100, say 100 units load is on node 3. So node 3 is a common node.
Mm-hmm.
And this node 3 will be in all partition, right?
Yeah, if the nodes 3 are shared, the nodes 3 are
it is
closed partition.
So, but the load, if let's say if the load 100 is on node 3, so
Right.
that 100 will go for only one of the partition.
Yeah, it should go just in one of the partition. So if the 100 load in both partition, then it will be counted twice.
Okay, thank you.
Okay. If there are no questions anymore, or like if there are any questions, let us know now. Like otherwise, we'll wrap it up. Thank you, Minji, for answering the questions patiently, and thank you, Michael Scott, like for the interesting insight, reminding us.
Sure.
And yeah, thank you everyone for attending. And next week, sorry, not next week, on 5th, we will see you guys again. This time, Ken Elwood from University of Auckland will be presenting. He's a professor here. And I think Michael Scott knows him, his colleague or his, you guys.
Yeah, grad school
Yeah.
contemporaries. Yeah.
Yeah.
What is he going to be presenting on?